Hello. So our project was the electric power consumption prediction model, and our team members were myself, I'm Joaquin, Sebastian, Justin, and Chris. So to give the motivation behind this project, energy is a huge part of the world today, and definitely the future as well. As you can see on the right, our energy usage over the years has only gone up. This is for all sources of energy, but electricity is going to be an even larger portion of that in the future, especially when it comes to things like sustainability, population growth, and technological advancement. Like LLMs are a huge part of our energy consumption today. In general, information is power. So why would our model be useful? And a lot of it is kind of getting forecasting of how much energy we'll be using in the future. That's super important for things like grid stability, so there aren't outages randomly occurring. Cost savings, so you know when is the most cost efficient time to be charging. And disaster preparedness, because if there's a natural disaster, having some baseline forecasting for how much energy an area needs can be really useful. So for our data set, we opted to use a city in Morocco named Tetouan. It has approximately 380,000 people living in it. This data set was great because it was one of the few public data sets that has large scale power consumption. And also it had very detailed information. So they collected the power consumption, or they collected feature vectors rather, every 10 minutes for a full year. So there were plenty of data points to train on. And those feature vectors included the power consumption in kilowatt hours, and also things like the date time, the temperature, the wind speed, the humidity, anything that really, or what they deemed to be important in determining how much energy would be used that day. So for our model, we opted for a multi-layer perceptron, which has a visual diagram on the right. At a basic level, there are multiple layers of neurons. There's an input layer, there's one or more hidden layers, and there's also an output layer. And there are weighted connections between all the neurons that act as matrix multiplications, so that the MLP is able to learn patterns of the data through backpropagation. For our application, this is really important because we're doing forecasting, but some other areas where MLPs are very useful is image recognition and NLP. An extra portion of our MLP is that we decided to use Monte Carlo dropout, not for the training, but for the outputs. So what Monte Carlo dropout is essentially you randomly kill neurons within that multi-layer perceptron to estimate uncertainty in the neural network predictions. So you'll run the predictions with different neurons being killed. So each of your outputs are slightly different. And from there, you can generate an empirical distribution of predictions, and you kind of get an idea of what the uncertainty is. So from there, we can get the mean and standard deviation, which we'll talk about later how that's useful. As for model training, we could not find a helpful or usable pre-trained model online, so we opted to train it ourselves. We decided to use Python because it's very approachable and very iterative, so that we could parse the data and go through different training schemes very quickly. So we opted to go with TensorFlow. We had one input layer, 3 hidden layers, and 1 output layer. We trained it without dropout because our goal using dropout was for uncertainty rather than preventing overfitting. And we had a test R squared of 0.92, which suggests that our model is fairly good at forecasting.
And to jump into our baseline implementation, the very first thing was just to duplicate our created MLP in Python into synthesizable C++ code so we can run it on the FPGA. And to talk about the dropout, we were able to tune how much dropout we wanted, and ultimately kind of went with a approach of having a dropout rate of 0.4%, 0.6%, 0.8%, and 1% respectively, with no dropout on the final layer since it only had one output. And these numbers may seem small, but they incrementally affect each other, so these small percentages actually have a large effect on the actual outputs. And we also implemented a synthesizable pseudo-random generation of dropout masks using a linear feedback shift register. Since there aren't really that many packages that are synthesizable in HLS for random numbers, so we kind of created our own. And to dive into the figure on the right side, basically with our CPU, we're going to be sending in the test data. The FPGA is going to generate those random numbers, jump through each of the 5 layers, and calculate a mean and standard deviation based on all the iterations in the Monte Carlo dropout. So with ours, we went with 100 different iterations, and we can calculate those and output those as a prediction. Next, with the optimization strategy, we really wanted to find a way to achieve a lot of parallelism so we can do operations at the same time to lower our time. And so looking at the figure on the right, the very first things that we noticed were, one, our dense layers were very expensive, so we wanted to figure out a way to lower the computation time of those dense layers. Additionally, everything on that right side runs 100 times because of our Monte Carlo dropout. So we definitely wanted to find a way to have those run in parallel since they did not depend on each other to lower the time as well. And lastly, we wanted to optimize the cost of generation of random bit masks for dropout. This was something that was only really done once and not iterated through with the Monte Carlo dropout, but was still expensive, and we wanted to find a way to optimize that as well. And to jump into the actual optimizations that we were able to make, we can see on the right the figures that we definitely made a lot of improvements and still stay within the area constraints, well within the area constraints actually, which was great since we wouldn't have any weird outcomes on the FPGA due to being too close to the actual constraint. And so with the actual key optimizations, the very first thing that we found most important was optimizing our bit widths. In our baseline implementation, we were using floats and 64-bit numbers, which was definitely not good. And we were able to limit our bit widths to 25 bits and 18 bits, which was extremely important for our usage of DSPs, since DSPs were able to multiply 25-bit and 18-bit numbers very efficiently, and anything past that was becoming a big issue. So by being able to limit our bit widths, we were able to push the program much farther without worrying about the area. And so we were also able to pipeline the calculation of the dense layers with an II of 1. This sped up the process significantly, and that can be seen on the figure on the right. And we were also able to fully unroll the inner loop of the generation of random matrices. And lastly, we were able to unroll the Monte Carlo runs by a factor of 2. It wasn't possible to fully unroll it just because of how much hardware would be needed to do that. But this is an area that definitely could be improved if we were using a slightly more powerful FPGA. Fully unrolling the Monte Carlo runs would make this significantly faster. Lastly, talk about some evaluation metrics. So first, it's important for us to define what we deem is correct. Since the test data and kind of the system we have isn't necessarily discrete, our accuracy isn't like being exactly on the money with what the actual value was. So to define correctness, we decided to say that a value was correct if it was within 1 standard deviation of the actual mean. So in our cases, we were able to get about an accuracy of at least 90%, which we thought was fantastic. And in our simulations, it was the same every single time because of our seeding, but actually running on the FPGA, they were different every single time because of the random generation. So the first time we ran the program, it was the same simulation, but afterwards it was slightly changed. However, these changes were very, very minute, and they still stayed within that 90% range, which we found fantastic. And jump in kind of like the speed up that we saw. On the software, we saw a speed up around 135 times, and on the FPGA, a slightly lower speed up of 133 times, which we thought was fantastic. There wasn't much of a difference between the two, and the accuracy still stayed the same. So there was no cost to our FPGA usage, which is fantastic. And we can jump into the demo to talk a little bit about how this actually works. To show a demo of our code in action, here's the output file for when we run it on the simulation. So when we run our simulation, it'll output a file here that'll show all the results of our test cases. So for example, it'll output the mean, which is our guess here for the amount of power consumed, the standard deviation, which is based on the Monte Carlo dropout, and the actual ground truth value, so we can determine if we are within the range to consider an accurate guess. So in this example here, we have 31,533 as our expected value, a standard deviation of 4,104, and the actual ground truth value is 32,985. So based on our calculations, that would be a success because it's within the standard deviation. And so you can see all the values here, or all the test cases here, are covered, and we have some advanced metrics at the bottom, such as having a total accuracy, which we can see is just about 90.67%, and an average distance from the expected value, which we get at just about 1600. And so this, for our purposes, we felt was accurate enough, given that we're trying to predict the power consumption of a city, which is not that easy to predict. And we can also run this on the FPGA by running the make FPGA command. And the values here are going to be slightly different because the random generation is going to cause there to be different outputs every single time. And so since I've been running this multiple times, that's going to give different answers. And so the values will still be relatively in the same range, which is exactly what we're looking for. So we can guarantee that they're actually working, but they're going to be slightly different. So for example here, we can just look at this last case. Our mean here is 23,452, and here on the FPGA is 23,520, which are close enough. And the standard deviation is about 2,600 in our simulation and 2,200 on our FPGA. So we can see that the values are close, but not exactly the same. But we can ensure here that these are actually the same types of predictions. Just happens to be that the random part or Monte Carlo dropout is causing it to be different. So yes, both of our implementations are working here, and we can see that there is about 640 millisecond execution time, which results in about 132 times speed up on the FPGA, which compared to our 134 times speed up on the simulation is fantastic.